Okay, so we got here last time. Let's do a little review of the we're starting into components. And remember, this is going to be the big thing for how you are going to figure out your field mechanics. So I'm going to put a vector into the first quadrant. We're just going to call this an electric field vector. I'm going to, well, I'm just going to start spraying an Adderall mist over this row before class starts.
Adderall. I don't think we need Adderall.
I think you do. All right.
So let's get these guys ready.
That's not how the chemistry of hyperactive disorder works. Yeah, I know you don't have attention. Trust me. Okay, so we have an electric field into the first quadrant. Now remember, when we get the first quadrant component equations, these are going to be your general equations. So like for example, remember we said any vector that you measure counterclockwise from the positive x-axis, you could put that angle anywhere from like 0 up to 360. You could put that angle into the generalized equations and get the proper exponent. So fine, if you can figure that out, great. Otherwise, you're going to build your right triangle, figure out your components, look at where the vector is, and you're going to know which component has to be positive, which has to be negative. Because why, like any component vector going up this way is going to have a positive y. Anything down this way is a negative y. Anything over here is going to be a negative x. Anything over here is a positive x. You just kind of get the idea of what they're going to be based on where they are. Because usually you're setting, it does help, and you'll see me do this in exercises. It does help to set a positive x and y. That way you can keep track of which way the vectors are pointing. Now, you talk about sine and cosine. Again, remember tangent's going to come into play when we talk about the direction that a vector sits at. When you look in the textbook, it'll say find the magnitude and direction of a vector. Well, they just want to know what angle it's at. Okay. And so if we want to know the components, which are going to be your y component is the one that's going up there. Your x component is the one going to the right. So remember, if we looked at our x component, the x component touches the angle theta. So that's adjacent. That's going to be your cosine. Your y component is directly across from your angle. That's opposite. That's going to be your sine. So that's where we get back to okay. So, and again, these are your generalized formulas for your components. That E value there, you remember what that was? So let's say this is an electric field vector. Magnitude. So remember, you're going to multiply the cosine or the sine by the magnitude of the vector. And we'll talk about what that means. Usually, like problems will say something like you have a magnetic or an electric field of, I don't know, 750 newtons per coulomb. Well, that would be the magnitude because it's not giving you a vector. And you'll be able to really identify why once we talk about vector component form. Okay, but let's say oh, how do I want to do this? Okay, let's redraw this electric field. And this time, I want to put angle phi there. You can still figure this out. So your components, of course, I just chose to make my right triangle there. There are several different ways you could go about this. I could just use the angle phi and figure out the components. So your EX, based on where it's at this time, is it going to be sine or cosine? Sine. You see how it's opposite from the angle phi? So opposite, it's directly across from phi. That tells you this has to be the sine function. So you could just do EX. And now here's a little cheating mode you can use. Once you figure out one of the components, the other component just has to be the other trig function. You don't necessarily need to look at the triangle again and go, is that sine or cosine? Well, you already found out this one's sine, the other one has to be cosine. But you could also, if you wanted to look at it, you see the EY in this case is adjacent to the angle phi. So I have to use cosine. If I wanted to use the generalized formats, okay, well, phi, how do I find phi if I wanted to use the generalized equations? Or, well, let's go ahead and put theta back in here. How do I figure that out? Yeah. So just for fun, I mean, if we put 90 minus theta in for phi into these components we just found, does anyone see the trigonometric identity? Sine of 90 minus theta equals what? Well, 90 minus theta is phi, but what is the trig identity? Sine of 90 minus theta is what? That is the definition of cosine of theta. So it might help you to look on the internet and find yourself a trig identity page, because a lot of these you can just go, oh, it's this, and you can simplify your work. So then your y component would be cosine. I hope you know what that cosine becomes. Sine of theta. So yeah, we end up, if we figured out theta, if we took 90, I don't know, because you could reverse that too. It's like your theta would be 90 minus phi. So if you had that, you can figure out what theta is and go right back to your generalized formats for your components. A lot of this can give you a lot to think about. That's why I always suggest just building your right triangle, figuring out your components, and then seeing where the vector is. If you just put your right triangle down, you can figure these out. I think that's really the most straightforward way to do it. And so let's kind of think about how I don't know, how units work here. Let's say, for example, let's use this one and this one. Let's say I told you your electric field, 9.5 newtons per coulomb. You're going to get used to coulomb. That's the SI unit for charge. And then what if theta is 57 degrees? Now, I know you've heard this before because they make memes about it. Just unless you know we're using radians, make sure your calculator is in degrees or you're going to have a bad time. So let's look at if I did EX. So you see here, there's no arrow on top of the E, and it just gives me a number. It just gives me a size. That's the magnitude of the vector. Again, when we get to vector component form, compare the two, you'll see how they're different. you'll be able to see that's a magnitude. So what you would do, 9.5 newtons per coulomb. Cosine of 57 degrees, the number you should get, 5.17. And then the only part of this that has a unit is the electric field, so you just bring down the newtons per coulomb. And that would be the X component of this field. Your EY, again, would be your 9.5. Newtons per coulomb, sine 57 degrees. When you calculate that, you should get about 7.97 newtons per coulomb. So for those of you who are just coming in this semester, someone tell them what the Newton is. Yeah, it's the unit of force. I was going to say it's not a cookie made from Middle Eastern fruits, but I don't know if anyone would get that. They are not. No, I do like them. So just for fun, let's look at a vector in another quadrant. Let's put one over here. Okay, let's see. Okay, so we are going to do this 3 different ways. We have angles theta, phi, and gamma. Theta is clockwise up from the negative x-axis. Phi is counterclockwise from the positive y-axis, and gamma is counterclockwise from the positive x-axis. So it doesn't matter which side you build your right triangle on. These are the same x and y components. Okay. And then you're told. Now, 2 ways to look at magnitude. I just want you to realize what these mean. So one way that you can actually write magnitude is like that. The magnitude of the electric field is just your symbol without your arrow. And in this case, we're going to make it 7.2 newtons per coulomb. And then we're going to make gamma 132 degrees. Look at where the electric field vector is. Does 132 degrees seem possible? Why? Right. The 132 exists between 90 and 180. So, I mean, you can always look and say, is that even feasible? Because if I had put in here gamma is 270, well, that wouldn't make any sense. Yep. Just to want to make sure you know your angles. So around your quadrants, it's 90, 180. Yeah, 270. Yeah, so 270 and then 360 back to 0. So let's figure out these components using all 3 angles. So first off, we have gamma, the counterclockwise from the positive x-axis. If we have that, we can just say, oh, let's just use the standardized component equations. So that means Well, let's make sure we understand. Going to calculate from gamma. Now let's see. So it's going to be E cosine of gamma. So we can just, since we have that angle from the positive x-axis, we can just go ahead and use the standardized equations. So your EX is going to be now you notice here using that gamma, I automatically got the correct sign on the X component. Does the X component being negative make sense? Yep. Because remember, we're going to set positive Y, positive X there. That means that the X component is pointing in the negative direction. Oh, so this one, so then your EY and this one should give you about. So like we talked about on Monday, you see that using the angle counterclockwise from the positive x-axis will automatically give you the correct signs on your components. Otherwise, you're going to have to analyze what quadrant your vector is in and decide what signs your components are going to have. Okay. Do what? Yeah, any quadrant you're in. Yeah, well, so try putting an angle in there greater than 180 for the sign. You'll get a negative sign. Oh. Not if you're measuring from the positive x-axis counterclockwise. Well, that was very close. There we go. Hey, now, what if we calculated using theta? Okay, well, let's look at this. Now we're going to look at the two right triangles. Your components are either going to be sine or cosine every time. You just got to look at where the angle is. So what are we going to use for EX here? Look at theta, look at where it's at. Cosine, because the x-axis is adjacent to the angle theta. So if we did that, we would get 7.2 newtons per coulomb cosine. Oh, but hang on. We don't have angle theta. What do? We only have the 132 for gamma. There you go. Now, let's talk about how we could put this 48 in there. You know that angle theta has a magnitude of 48 degrees. You could just put the 48 straight in there. You already see that the x is pointing that way, so it's going to have to be negative no matter what you do by the way it's pointing. However, what's another way we could write that 48 to automatically get the correct sign? Nope. Which way, if you're traveling from theta to your vector, which way are you moving? Why is it negative? Clockwise motion. But technically that's a negative 48 degrees. Remember, clockwise motion, negative angle. Counterclockwise motion, positive angle. Yeah, you could put it in as negative 48. You could just put the 48 in there, get the number, then you see which way the x component pointed. It has to be negative. So another way I did it, I put the 48 in. When you calculate this, newtons per coulomb. However, I see that the vector points that way. It has to be a negative. It has to be a negative component. So let's look at, well, if EX was the cosine, that one has to be the sine automatically. And so when you put your numbers in again, you're going to get 5.35 newtons per coulomb. Am I going to leave that one positive or should it be negative? Positive, because it's pointing in the positive y direction. Mm-hmm. Well, because when you're measuring from the positive x-axis counterclockwise, no matter what the angle is, use the generalized equations, which is cosine for x and sine for y. You use it every time. And whatever angle you have, if you're measuring counterclockwise from that positive x-axis, will automatically give you the proper sign on the component. All right, let's try. Now let's try it with phi. Okay, so we figured out theta, we know gamma. How do we get phi? So that one has to be 42. Again, a lot of this is going to take practice because if you're thinking, if let's say you latched onto that moving clockwise, then you would say, you might be going, well, it's a minus 48. No. That's going to give you an obtuse angle. Theta, you have to look, you say theta and phi both exist within a 90-degree quadrant. Neither one of them can be over 90 degrees, and the two of them together have to equal a total of 90 degrees magnitude. So as you practice, this stuff becomes more intuitive. Okay, so let's look at this one. What trig function are we going to use for EX? Sine, because the X is opposite from the angle. Again, because we used an acute angle, we're going to get a positive sign, but we know that X points in the negative direction. So we change its sign to negative. I could figure it out using the right triangle, but I already know that X uses sine, which means by default, Y has to use the cosine. So it doesn't matter what angle we use, we're gonna get the same components. So let's take a few minutes working together. We'll take about 5 minutes. Work on this, see if you can figure it out. Yeah. Yeah, gonna have to be clockwise. Yeah, but, yeah, so. Gonna have to be clockwise, into the fourth quadrant. Well, estimated 30 degrees. This one I just set as a general force vector. So instead of newtons per coulomb, just use newtons. This thing is all crooked. I'm afraid to move it though, or shut the springs off. So theta is a clockwise motion into the quadrant. You can't even follow it. Well, let me, hang on. What I said it as. Oh yeah, but it looks like yeah, phi is counterclockwise from the positive x-axis. Yeah. Just forgot to write it in the problem. Counterclockwise from the positive x-axis, all the way around. You're going counterclockwise from the x-axis, you want to cosine equal x. The way you can think about it is anytime you have an angle counterclockwise from the positive x-axis, it's like solving a vector in the first quadrant. So first off, your vector is going to be there. We're going to call that our generalized force vector. It's going to have components. I'm going to set positive x and positive y. And then my theta is that angle right there. So my phi right there. So let's look at theta. Need the magnitude of the force vector. Which trig function are we going to use for x? Cosine. So I'm just going to go ahead and put the negative 30 in there because it's in the problem. I'm going to get 4.24 newtons. No matter what I calculate, I'm going to leave that positive because the x component is pointing in the positive x direction. So I switch to sine for the y component. And what do I get for this one? Again, no matter what you get, you're going to put a negative sign on it because it's pointing in the negative y direction. Now, what about using phi? What does phi equal? Yep, so it's going to be 360 minus theta. And so we're using magnitudes here because, again, we can't have an angle greater than 360. So we're just going to take 30 off of the 360. So we're going to be using 330 degrees. If you remember what your limits are, sometimes that helps. Like, again, like I just said, if you come up with an angle greater than 360, that's physically impossible. So try looking at it a different way. For this one, since it's measured from the positive x-axis, we're just going to use our generalized equations. And I'm sure you noticed that your calculator very conveniently gave you the proper signs when using the angle from the positive y-axis. You what? Well, find it again. Oh, did you? Well, how? I thought you said you found something slightly different. Oh, okay. I thought you said I found something slightly different. I was like, well, that's not going to cut it. Oh, okay. Yeah, you will. Okay, let's start talking about the magnitude of a vector and its direction. Okay. First off, these equations are going to be very generalized. All right. When we say magnitude of a vector, this is what we mean. So you can look at it based on the Pythagorean theorem, or you can just remember the formula. We've been calculating x's and y's. So let's say you have the x and y, you want to know how big the vector is. You plug them in there. That is the magnitude of a vector. The direction of a vector is going to be this inverse tangent y over x. Make sure on your calculator you're using the tangent to the -1 button. Please don't use cotangent. You don't say, look, 1/tangent, so it's gonna be cotangent code. You can see your calculator can go fast if you start trying to do fancy stuff. The reason it is this way. Let's say we have a vector. We have our angle theta. But see, we don't actually know what the magnitude of that vector is, but we know EX and we know EY. So I'm hoping you realize that tangent is the function that relates opposite and adjacent. So this time, if the vector is always the hypotenuse of your right triangle. This time we're saying tangent theta. And what is, so what do we say tangent theta was? It's what over what? Opposite over adjacent. Opposite EY over adjacent EX. And so then you just take the inverse tangent of each side. And you get the, and so this, when something in the textbook says, what's the direction of the vector? This is what it's asking. Now, as we work through assignments and you start to get used to, these directions, you'll figure out where the angles go when you're looking at your vectors. It takes a little practice. You know, I think I had something planned for this slide. I just used too little space. Okay. So let's say you experience a force from the electric field exerted by a positively charged particle. This force has components, Fx 85 newtons. Well, I've got to stop changing my notation. Force in the y direction, -132 newtons. What are the magnitude and direction of this force? Well, first off, what quadrant am I going to draw this force vector in? Fourth, why? -y, +x has to be fourth quadrant. Now, is it going to be closer to the y-axis or the x-axis? The x, because you see how much larger magnitude-wise the y component is? So that means it's going to have to go down further this way. And so then we can say, well, let's figure out its magnitude. We always start with the theorem. Who's seen that notation before? Yeah, so when you have an exponent of 1/2, that's the square root. And so that's how, so it's like it's how it works with the exponent fractional exponents. Exponent of 1/3 is the cube root, so on and so forth. So that's, I just think it's an easier way to write it. My what? So do you see, let's just talk about magnitude, sizes, not negative or positive. You see how much bigger the y component is than the x component? That means the y component is going to go a lot further down than the x component does out. So then from here, Your magnitude should always come out as positive numbers. So when you use your calculator, you should get about 157 newtons. So let's talk about the direction. Theta. And the great thing about these is we're just going to use these equations. We don't even necessarily have to build a triangle. This magnitude and direction, they're going to be pretty standard. You know, not in force. And so that's going to be a negative 132 over 85. Your theta should come out to be negative 57.2 degrees. Now, if you didn't realize it, if you were going, well, which angle is that? First off, it's a negative angle, so it's a clockwise direction. We know it has to be there. If you forgot that, you would say, well, how big is theta? Like, what's its magnitude? Well, its magnitude is greater than 45 degrees. Any vector at 45 degrees in a quadrant is just going to go straight corner to corner. That corner to corner is 45 degrees. So if it's greater than 45 degrees, it has to be lower, it has to be further than that corner to corner. So you're looking for the larger angle. That's going to have to be your theta. You'll practice these as time goes on. You'll get used to them. You will, yes. Oh, yeah. What? Not you. You'll get one on Friday.
Oh, but it's due next Friday.
Yeah, your first quiz will be next Friday. Well, next Thursday. Remember, you're taking exams and quizzes on Thursdays and lab. Well, I would prefer it, yes, because I want to make sure we go over, we go over all this stuff, because again, it's not strong electricity, but it is electricity.
So allowed to be able to search for the allowed, but not for.
Yeah, on the exam, yeah, exam is no last.
Also, I have a question.
Yeah. Let me shut this off.
None of your fault.